Hello and welcome to my video for notes on simplifying radicals. I'm going to start with a little brief intro here. The reason this is what we're learning today is because next week we are going to talk about the quadratic formula, and in the quadratic formula there's going to be some places where we need to simplify radicals. So I know it seems kind of random because we've been doing a lot of factoring, and then we did solving by factoring. This is just like a little piece to the quadratic formula puzzle, and so I kind of like to intro simplifying radicals before we get to fully doing the quadratic formula. So just a couple review things here with this little graphic. A radical, that's that fancy little squiggle bar thing that goes over the radicand. The radicand is the number, or it can be a number of variables, whatever, that goes underneath it. We would call this radical a square root because there's no number here. Sometimes you can see a radical that has a number in there. So this would be called the cubed root. They have, you can go up to the fourth root. You can go up to a bunch of different numbers, but we are going to focus on square root. It is just understood that even though there's not a little 2 right here, that's a square root. So we're going to be focusing on square roots today. So know that it's understood that there does not need to be a little 2 there. Everybody just knows a radical without a number is a square root. We're going to jump right into some examples here. So we're going to be simplifying all of these different examples. In order for a radical to be simplified, it must not have any perfect square factors in the radicand. So radicand, number under the square root, there cannot be any perfect square factors in there. We're going to be dealing with a lot of perfect squares, and I'm going to say perfect squares a lot. So I think it's going to be the most helpful if we list out the perfect squares over to the side to kind of reference those as we're working through these problems. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25. I'm going to list out a few so that we have something to reference, and this is always a handy thing to do anytime you're dealing with perfect squares or square rooting things or stuff like that. Let's see, 7 times 7, 8 times 8, 9 times 9. And we get 100, 121, 144. I think I'm going to stop there because I don't think we go any further than that. No, we don't even get that close. Okay. So first example, the square root of 16. Square root of 16. So we're looking for a way to simplify that, and our steps for simplifying radicals are going to be find the biggest perfect square of the radicand. Well, the square root of 16 is a perfect square, and we know that the square root of it would be 4. So if we have a perfect square already under the radical, we want to simplify it right away, and then we're good to go. Example 2, the square root of 125. 125 is not on my list over here. It is not a perfect square on its own. So there's going to be a way that we can break it down and simplify it. I want to start and look through my list over here and see if there are any perfect square factors that fit into 125. And I know that 25 goes into 125. So we pick the biggest perfect square that's a factor of the radicand, and then we're going to split it into those 2 factors. They're still under the radical though. So I split it into the square root of 25 times the square root of 5. So we just split it into its biggest perfect square and then the factor that matches with it. And then to finally simplify the problem, we would actually take the square root of 25 since it's a perfect square, and that would be 5. And then 5 we can't simplify any further under the radical, so we leave it alone. So your answer simplifies to 5 square root 5. Example 3, the square root of 32. I want to see what I can split that into. I want to pick the biggest perfect square. So up here in these steps, step number 1, find the biggest perfect square factor of the radicand. So the biggest perfect square factor would be, let's see, I know 4 goes into 32, 4 times 8. But I'm going to keep checking factors because I want to make sure it's the biggest perfect square. So 4, 9 does not go into 32. 16 does. It's 16 times 2. And then all the other factors are bigger. So 16 times 2 is the pair I want to go with. So I'm going to split into those two products, or into those two factors, and make them a product. I can take the square root of 16, that's 4, and then I leave the square root of 2 the same. So my original square root of 32 radical can be simplified into this 4 square root 2. So 4 times the square root of 2. Let's say, just for this one example, let's say I picked 4 and 8 instead, and I said, okay, so I can split it into the square root of 4 times the square root of 8, and then I get 2 square root 8. I can't stop there because it's not as simplified as possible. So you have to make sure your radicand does not have any other perfect square factors remaining in it. And 8 does have a perfect square factor still. It's 4 times 2. So let's say I kept going and I get 8 split into the square root of 4 times the square root of 2, and I still have my 2 out in front because it didn't go anywhere. My next step would be to take the square root of 4, and with this constant out in front, I would multiply those two together, so I get 4 square root 2. So I got the same result, it just took me an extra step. That's why it's the most helpful if we start out by picking the largest perfect square to begin with. Now this column over here on this side, the intensity increases a little bit in our simplifying radicals. So here you see I have a constant in front of my square root of 54. I have 5 square root 54. We're going to simplify the radical first, the same way we have with our other examples. So I want to see, and I'm going to leave that 5 out there in the front for my product so I don't forget about it. But I want to see what I can split 54 into where it would have the biggest perfect square. So I'm going to look down my list, and in my list, 54 divided by 4, that does not give me an even number. 54 divided by 9 gives me 6. So 9 and 6 would be my options for factors for 54. 16 does not divide evenly. 25 doesn't go in there evenly. 36, and then we get closer and closer to 54. So it's got to be 9 and 6. So I can't forget that I have this constant out here, but my next step needs to be to simplify the square root of 9, which would be 3. So I would end up with 5 times 3 square root 6. And then finally, to complete this problem, we would just multiply 5 times 3, which gives us 15 square root 6. Example 5 has a quotient. So I have 10 plus the square root of 48 in the numerator, and then we're dividing that by 2. I Still want to start by simplifying the radical first. That just makes everything a lot easier. So we're going to take the square root of 48 over here, and I'm going to see how I simplify it. I'm going to look at my perfect square list. So 4, I know that 4 times 12 would give me 48, but I think there's probably a bigger factor that would go into it. 9 does not go in evenly. 16 does go in evenly. 16 times 3. And that is going to be the biggest factor, the biggest perfect square factor that goes in to 48. So I'm going to split that into those two factors and take the square root of both, keep them under the radical, and then I know simplifying the square root of 16 would be 4. So I'm going to rewrite my whole quotient now as 10 plus 4 square root 3 over 2. Hopefully you're thinking, I think there's a way I can keep simplifying, and there is. Since we have that whole numerator that is divided by 2, we can simplify one step further. We can take 10 divided by 2 and take 4 square root 3 divided by 2 and simplify one more time. You have to make sure that you can evenly divide both. If I wasn't able to evenly divide both, I could simplify 10 over 2, but if 4 was maybe a 5, then I would write it as a fraction, and I can show that later. But here we've got 10 divided by 2 is 5. I want to keep the addition symbol that's in between the binomial that's at the top. And then when I simplify 4 square root 3 over 2, since 2 is not under a square root, it's just a number, I can only divide 4 divided by 2. I don't mess with the square root 3 at all. So we're going to keep 4 divided by 2 is 2, and then we just keep the square root 3. It doesn't change at all. We can't divide it by 2 because it's under a square root. It's not a like term. So we would leave our answer, and our final answer would be 5 plus 2 square root 3. The last example we have here, 14 minus the square root of 49 over 7. I know it's probably very tempting to go ahead and divide 14 by 7, but I need you to simplify the radical first. So this one ends up being like a nice, pretty answer because 49 is right here. It's on our list of perfect squares. So if we have, oops, I didn't mean to do that yet. So if we go ahead and simplify it, we've got 14 minus 7, and then it's all over 7. Since that radical's gone, we don't have any more square root, we can actually go ahead and just simplify the top, and we would get 7 over 7, which is 1. So we get a nice little pretty answer there. So we always want to simplify the radical first, and then we start simplifying our quotient after that. One more thing that I want to show you that I kind of mentioned up above. Let's say I already simplified my answer, and this is the radical that I had. As the quotient, we can go ahead and continue to simplify because 5 divided by 5 is a nice even simplification. So 5 divided by 5 is 1. Now 3 square root 2 over 5 does not simplify as well. But the way we would write it is we just keep it as a fraction, put 3 square root 2 over 5, and then we're done. So that would be your final answer. One other thing is I'll use my square root 125 example. Let's say I had written it in the other order, and I did square root 5 times the square root of 25. And I simplify, and I get the square root of 5 times 5. my answer isn't done until I move that constant to the front. It's just the most simplified way to write your answer, and it's the way that makes the most sense. So we want to move that constant out to the front before we box in our answer. I'm going to put some practice problems on a separate sheet with an answer key on Canvas that you guys can look at. You can always email me if you have any questions. You'll just be doing a short little skills check over simplifying radicals this week to end your